Okay. Also, so if we care only about the predictive performance, if we think about this concrete quality or medical cases, if we only care that our predictive performance is the best, we then just include all prior information, integrate over all uncertainties, no need for feature selection. So only if we need to reduce measurement cost or computation cost in the future, or we need to improve explainability, then we might want to do variable selection. We might want to find a minimal subset of features that yield a good predictive model in a way that what would be that in a way that we would minimize then also the cost in the future or cost of explaining. But sometimes we might also be interested in identifying all features that have predictive information. And I'm now in this here talking more about this minimal subset selection. So that was the same. There are also cases where in a lot of papers recommend such that add some kind of shrinkage prior or have that kind of model that there's some probability, finite probability also for coefficient to be exactly 0, so no effect, and then some probability that it has some non-zero value, or continuous shrinkage prior which favors values near to 0, and then looking at the marginal posteriors of these coefficients make the variable selection. But this doesn't solve the problem. Even if that shrinkage prior would correspond to your actual prior information, it has limitations. I already saw you an example where the marginal posteriors were overlapping 0 because there was a correlation in these covariates, and then we had to look the joint. But if we have many variables, it's difficult to look the joint over the many variables. Another thing is then there's also a problem that if we do the selection, how we do the post-selection inference correctly. Here's an example showing the problem that why the marginal approach can be difficult in higher dimensions than in just 2. We have some latent feature f, which just comes from normal distribution. We have y, which is noisy observations given that latent f, but we don't observe that latent f directly. Instead, we observe noisy covariates features, and then in this case now these xj, they depend on f, but also they have jointly because they all depend on f and they then have some noise, they are actually correlating. So they are noisy versions of f, and now this raw determines also how similar they are to f, but also how highly they are correlating. And in addition, we have then completely irrelevant xj's, just pure noise. And now we would like to then do a model variable selection so that we would find only these relevant variables. Now we have 25 relevant, 25 completely irrelevant ones. And then generate small data with certain correlation. Here we use Gaussian prior, and these are the showing posterior median with 50% and 90% intervals. and we can't see, all the intervals are overlapping, so we are not able to see which ones are relevant and which are not. This is horseshoe prior, which is such that it's very narrow, so a lot of posterior mass near zero, and then very thick tails. It aims to make then, the idea is that the irrelevant variables would get also in posterior shrunk towards near zero, and relevant variables, because the prior has thick tails, can also have large values. But again, we can't see where those relevant ones are. Spike and slab, so having this, that there's a finite probability that weight is exactly zero, and then we are computing these probabilities that, what's the probability that it is non-zero? And we can see there's only one which goes beyond 50% of probability being included. And this can be also explained by that, since we had 25 very highly correlating variables, it's likely that we don't need them all to already make reasonable predictions. Additional correlating variables don't increase the predictive performance much. And if we can manage with less, it means that this inclusion probability stays quite low. And it's difficult to see again which would be relevant and which are irrelevant. And so half of the features were relevant, but all marginals are substantially overlapping with zero. We can look also what happened in this same illustrating, what if we start with just having two relevant variables? That's easier task. Even then so this was the kind of what I had before. Marginals are overlapping. Jointly we could see that they are away from zero. But when we get more and more variables, it gets more and more difficult to see from the marginals. It's not enough to look 2D joint distributions, and it's very difficult to look this in 50 dimensions, which would be the relevant ones. But we can do better approach so that let's make first the best predictive model we can. It's called reference model, and then conditional on that, we do variable selection. And the good point here is now this, that we are conditioning on this to some model, and we know that modeling reduces noise. And then also this happens to also give us what to do after making the selection. And then we can find the minimal subset of features which have almost the same predictive performance as the reference model. Why the reference, kind of the illustration that why the reference model helps. Here, it's the same data generating mechanism. We have just now more variables, 500. 150 of them are relevant, a bit less correlation, 0.5. And these blue and red dots are sample correlation of each covariate with target variable y. And I then have with the blue are the irrelevant ones, and with the red are the relevant ones. We can see that on average, red ones have higher correlation with the target variable, and the irrelevant ones have, on average, lower correlation. That's nice. But there's so much overlap. If you look at then the kernel density estimate for the distribution, so there's so much overlap that it's difficult to choose where we should put the threshold that we are including relevant variables, all the relevant variables, but not any of the irrelevant ones. There's a lot of overlap. However, if we now if we would also observe that unknown latent variable f, which was the noiseless, kind of the noiseless version of y, then the correlation between irrelevant and relevant, it's more easily to separate. So there's a bigger separation, less overlap. But we haven't observed f. But we can use all x's to make a model. So we use all x's and y to make a model and estimate f. And we get this f star. And now the benefit in the kind of the, when we were looking at these individual correlations, we were always looking just one x and one y, and there's a lot of noise. But if we use all x's together to make a model which predicts what is f, even if that model is not perfect, using all the information makes f star anyway better than just the noisy y. And we still get better separation between relevant and irrelevant. So that's key, that we can use. We may first build this best possible model to filter out noise, and then use that best possible models to do variable selection. I go a bit over time today, but this is also beyond the course, so you can also leave if you need to. So we start with the biggest model, and we then think that can we simplify that model? So we replace the full posterior distribution with some constraint Q, so that the predictive distribution changes as little as possible. And that constraint can be, for example, that what if we constrain that this coefficient is 0, so that we are not using information from this variable. So we could have also other cases that the Q could have only a point mass. So what would be optimal point estimate instead of integrating over? Or then, as I mentioned already, what if some of the features have exactly 0 regression coefficients? Which features can be discarded? And so this has the decision theoretic background, that given these kind of constraints, what is the optimal way to do the inference? Here's an example for the logistic regression with just 2 features. We have beta 1 and beta 2, and you see the posterior distribution. And then in addition, we have the prediction. So we have observed the class, red class and green class. And then when we have integrated over beta and beta 2, given that posterior distribution, here's our uncertainty that what class we would observe in the future given x1 and x2 values. This would be the optimal point estimate, so that if we would replace that integration, replace all these posterior draws with just one value, so we are looking at what would be that point estimate that would give as similar predictive distribution as the original. And then that blue cross gives us that this and these are as similar as possible. We could also then ask that, okay, it's a point estimate, but additionally, B1 has to be 0. This would be then the optimal value and optimal predictions. Or we can choose that B2 has to be 0. And now we could compare that, which one of these gives us better predictions. But instead of just looking at the point estimate, we can also project these posterior draws each posterior draw can be projected, but what if we would constrain beta 1s to be 0, what would be the projected posterior draws R? Or if we constrain P2 to be 0, and then we can compare which one of these constraints gives us better predictions. So we are replacing the full posterior with some constraint Q, so that the predictive distribution changes as little as possible. The good thing is now that we started from the this full predictive distribution from the full model, and we are looking at that constraint. We are optimizing these constraints only in comparison of that full model predictive distribution. So we can only overfit towards that one. So, but we are not able to overfit to the data anymore. And since we are optimizing towards that model result, it's similar as I saw that kind of that whether we are optimizing towards the correlation between X and Y or X and F star. As the full posterior is projected, the prior is also projected, which makes it also nice that we don't need to define the priors for submodels separately. Even if we constrain some coefficients to be 0, the predictive inference is conditioned on the information-related features, to those features, if they contributed to the reference model. So when we had a lot of correlating variables, all those correlated variables were able to predict F star better. And even if we then say that, okay, these are not used in the future, they helped us to make better coefficient estimates for the rest, which are still used. So we have now that we can include these constraints, but then we still need to also select that, okay, which constraints, which variables we put to the coefficients we put to 0. For a given model size, we can, if possible, we could go over all combinations, all variable combinations, and choose the one which has minimal projective loss. So given certain model size, so that we set the same number of coefficients to 0, which combination of setting zeros gives us predictive distribution which is as similar to full model as possible. Another part is then we need to also choose the model size, and then we can do these Monte Carlo search, forward search, L1 penalization searches to make it faster. We still need cross-validation to select the appropriate model size, need to cross-validate over search paths, but that's easy with the importance sampling. And I showed you previously similar figure. These, now the gray lines are what is the actual predictive performance with independent test data when we've done backward selection with different approaches, and you can see that with the cross-validation, so there's a lot of variation how good search paths we find, and all the time we are overfitting, giving worse predictive performance. But with the projection, we get very stable performance and also no overfit to the data, because we are doing this selection process now against our best reference model. Example with this is now just small p example. So less than 20 variables, 251 observations. The target value is what is the body fat percentage. One way to estimate is that we weight person first in air, then put the person in harness, and with the pulleys then lower that person to water, and immersed in water, wait again. And then based on that, we can compute density, like all the, we get the volume, how much, depending on kind of what's the difference of weight in air and water, we get the how much water was replaced, so volume of the person, and then we get the weight and the volume, we get the density, and then there's equation including the weight and density to compute body fat percentage. But of course this requires quite big equipment. You need to have big enough tub where you can immerse the person and have the weighting system. And then the question is that what if we just use a scale, so you get the weight and then different, with the tape measure the circumference here or here and here, and which places are the best to measure, or does it help that we measure in many different places to estimate this body fat percentage? So this one shows Siri is the equation used to convert from the density to body fat percentage, and that's our target value now. And the others are then these cheaper measurements. So weight using scale and height using tape measure, and then the rest, neck, chest, abdomen, and so on, are then circumference of that part. This is correlation plot, so we can see that Siri is correlated with many of these values, so definitely there's some information. But we can also see that these different circumference measurements are highly correlating with each other. So it's difficult to then, looking at the marginals, know which should be included. And if we look at the marginal postures of coefficients, so we see abdomen measurement, so around here, it's clearly away from 0, so that should be included. But then other marginals are mostly overlapping, and it's not clear. And it's also strange why there's so much uncertainty whether to include weight or not. Well, that's one reason is that weight and height are highly correlating. And it's understandable that, of course, tall people weight more without having actually higher the body fat. Here we can do the projection predictive variable selection. So there's a broad spread buckets in R. The first one is 0 variables, the 1, 2, 3 variables, and so on. And we can see that 2 variables would be enough to get similar predictive performance as all the variables. And they happen to be then abdomen and weight. Interesting was also here that for the body weight, the weight has a negative coefficient. Why? It's because conditionally knowing abdomen, the same persons that have the same abdomen circumference, those who weight more have less fat because fat is lighter than muscle. So it's always important to also, when looking at these, to remember that these are joint effects. Otherwise, if we would have only the weight alone, then persons who weight more are likely to have more body fat. But if we first know the abdomen circumference, then more weight is less fat. Project posture is not just a conditional of the joint, illustration of that. We can use it also for Gaussian graphical models. We have examples of going to higher dimensional. We can have one of the examples, we have 22,000 variables and only less than 100 observations. So works also well with small n, large p cases, and there's more results available in the references. Sparse priors are not enough alone. Reference model projection can improve feature selection a lot. We have already the packets for GLMs, and hopefully we soon have also updated packets which works with GAMs and multi-level hierarchical models. Kind of the theory is easy, but it always takes some time to implement these algorithms. And more details available. That's it.